All right, let's take a look at skill 4 and do these problems and see if that doesn't help you to prepare for the final. All right, so let's take a look at what we have here. State the approximate intervals on which the function is increasing and also decreasing. So I'm going to use a highlighter. I know that on this portion of the graph, that as you move from point to point, as you move to the right, you're going down to stay on the graph, so I know it's decreasing. And the same can be said here from this point down here. It's very steep, but as you go from left to right to stay on the graph, you're going down. So on these two intervals that I've highlighted in yellow, we're decreasing. In between here, if I highlight this in green, we're increasing. Now, at first we increase really quickly, and then it kind of almost levels off and becomes constant, but not quite constant. See, there's some people that argue a little bit that right here there's a portion of it that's constant, but if you zoomed in closer and closer and closer, you see that it only has one x-intercept. Then it continues to increase and go on. It's going through the origin, and that's it. So the yellow part is decreasing, the green part is increasing. All right. So our function is increasing. What's increasing is the y-coordinates, and the interval we want to describe is to say over this x interval for these values of x. As x increases, y increases. So the x-coordinate here is -3. So my function is increasing on the interval from -3. And if I come over here, this x-coordinate is +3. So that's what I've highlighted in green. Now this function is decreasing. On the interval, well, this arrow is indicating infinity, and remember I'm describing the x, so this arrow is going to the left at the same time going right if I break it up into x and y components. So from negative infinity all the way up to this -3, if you're on this portion of the graph that I've highlighted in yellow, the y, as x increases, the y values are decreasing. Or, and here's that union since there's a break, if you're from +3, from x equals 3, all the way down, hey, to again, actually I'm moving to the right. There, so that's the interval over which I'm increasing, highlighted in green. Here's the interval over which I'm decreasing, highlighted in yellow. Since it was two regions, we had a union there. That translates to the word or. All right, so determine if it's even, odd, or neither. Now, we had official definitions. If a function, if f of x is replaced with, we may have said a, -a is equal to f of a, if that's a true statement, then this function f is an even function. If the opposite of a is equal to the opposite of f of a, then it's an odd function. If neither one of these equations are true, then it's neither. Now, students have a difficult time with that official algebraic definition. We did enough of these that we begin to observe some shortcuts, some patterns, especially when we had a polynomial. We don't have any variables in a denominator. And we noticed that if this exponent's odd and this exponent's odd, and if you're not lifting the graph up or down, if this is +0, since both of those exponents are odd, this is an odd function. So on a final exam, that's going to be much faster. Now, if you can fast forward to the next problem. If I evaluate this function at -a, what do I have? Well, a negative base raised to an odd power, that's going to be a negative term. This is going to be negative, and I'm already subtracting So it changes to positive, and I have this. Well, clearly that's not equal to the original expression. So the opposite of the original expression, I would have negative 3a cubed plus 6a. Since these two equations are equal, it's an odd function. But like I say, it's a lot easier if you've noticed that pattern and that observation that both of these are odd. Now, had they made this some number like just a 1 or something different than 0, it would be neither. The odd functions have symmetry with respect to the origin. All right, this next one, my exponent is even. Now here it's less forgiving to this up and down. Remember, an even function is symmetric with respect to the y-axis. So if you had 4x squared, this graph, the minus 3 pushes that graph down 3 units, and it still has symmetry with respect to the y-axis. So adding and subtracting does not ruin the symmetry with respect to the y-axis like it would with respect to the origin. I've got an even exponent there on x. Doesn't matter whether if that's a 0 or a minus 3 or a plus 5 or a 1/2. Doesn't matter what we're adding. It's not going to ruin that symmetry. This graph is symmetric with respect to the y-axis. Officially, if you were doing it algebraically, if you evaluated this function at the opposite of a, then when you have this quantity negative a squared, negative a times the negative a is a positive a squared, and that's equal to the original function if we evaluated at a. Since it's true that f evaluated at negative a is equal to f of a, that implies it's an even function. But it's far easier and quicker if you notice that, hey, this exponent is even, I know my function is even. Well, here, and see, this works fantastic for polynomials. If we have a more complicated expression, these shortcuts may not always work. For this polynomial, we have an even function, but we also have an odd function. It's going to be neither. If you were to graph this, the graph of this is a parabola, and it's just that vertex is not at the origin. It's not through the y-axis. You know, this quadratic function is never going to be an odd function, and it's only an even function when the vertex is on the y-axis. When the x, when you have it move, if the vertex is 0, comma b, 0, comma something. All right. Hey, you just simply have to memorize these. The identity function, that's a 45-degree line. That means that for every x, the input, it's equal to an output. So if this were the number 2, then the y-coordinate would also be 2. If this is the coordinate negative 2, then at that point the y-coordinate is also negative 2. The input is identical to the output. That's why it's called the identity function, and that graph is right here, this guy in A. A constant function means the output is constant. Here, as x changes, the output is y. Y doesn't change, it remains constant. It's a horizontal line. Absolute value function looks like a V. It's opening upward here. If it opened downward, hey, you know, the coefficient would be negative in front of it. This is your parent function for an absolute value function. Squaring function, another term for a quadratic function. The graph looks like a parabola, and here it is, with the vertex centered located at the origin. Cubing function, it's right next to it here. If you have a value like 2 and you cube it, you'll see that 2, 8 is on there. If you have a number like -2 and you cube it, it'll be -8. So -2, -8 would be on the graph. Square root function, square root of 0 is 0, and it gradually increases. Here it is right here. Really, I'm just doing this for memorization. Now, if I had a scale on there, I could plug in a few points just to verify it. If this is out here at 4, the square root of 4 is 2. So you can kind of see that the relative size, the comparison there. Cube root, you can take the cube root of negative numbers. So here it is right next to it here, g. Exponential functions, that's some of the stuff we've recently done. Here's an exponential function where the base is bigger than 1, it's increasing. An exponential function also could look like this if the base was less than 1 for a decreasing function. But they typically just use the parent for increasing. Logarithm, here right, and see that how this has a horizontal asymptote of y equals 0. Then the domain and range switch for exponential logarithm, and the horizontal asymptote becomes a vertical asymptote. And here right next to it, we have the graph of a log function. The reciprocal, 1 over x, it's undefined. It has a domain of all real numbers except 0. And I should probably come through the identity function. The equation would be f of x equals x. Constant function, f of x is equal to some constant, call it c. Absolute value function, you know the symbols for absolute value. Squaring function, the exponent is 2, you're squaring this base. Cubing function, you're cubing it. Cube means an exponent of 3. Square root function, you know the symbol for a radical. A cube root, same radical symbol, only the index is 3. The index for a square root, it's implied that that's a 2. We typically don't write that. It's implied. Well, if that's implied, you have to specify that that's a 3 if you're taking a cube root. An exponential function, if we have some base, call it b. The variable is in an exponent. For a logarithm, we have log base b, the argument x. So here in function notation, this reciprocal function, f of x is equal to 1 over x. So you may be tested on it indirectly when it's talking about transformations, or it's just going to be to your advantage to know those equations and the title of those, and to match them up to the graphs. And it's just going to be memorization, whether you need some cue cards or hopefully it's just review. Hopefully you have some idea on a lot of these. All right, our transformations. I'm going to pause this for a second. All right, I believe this. I'm back and this is recording. I went and looked at Skill Packet 4 and copied and pasted the order of the transformations, because order is important. You just can't come in and start reflecting and shifting left or right or up and down without doing it in some kind of order. Now, there are different orders that will work. The order that we agreed to use, the order that I know will work every time, is first if you do horizontal shifts, which means shift the graph to the left or to the right first. Then look and see if there's a multiple in front of x. And remember, these first two are bizarre in their behavior. That +2 is actually a shift to the left 2, and had there been a number like 3x in front of here, it wouldn't have horizontally stretched it by 3. It would be a horizontal shrink by a factor of 1/3. So we also can include in this second step here, after you've done your shifts left or right, and if you shrink it or stretch it horizontally, you would then reflect it if there's a negative sign across the y-axis. Within that step 2, the compression and the reflection are interchangeable. The order there actually isn't important, but it is important that you do the shift left or right before you do either the compression or the reflection. So those you'll notice horizontal, those are affecting the domain. Here in steps 3 and 4, you're affecting outside of the function, you're affecting the range values, and you do it in a normal way. It's not bizarre. You do multiplication before you do addition or subtraction. The vertical stretches and compressions are, if you multiplied it by 2, hey, that'd be a vertical stretch by 2. If you multiplied it by 1/2, that'd be a vertical shrink. What's bizarre, I guess, is the description of the reflections. To have a negative sign out in front here, to take the opposite of the output, is actually a reflection across the x-axis. And look, see, it says reflection across the x-axis. It's interchangeable whether you did these vertical compressions, which could be a stretch or a shrink. That's what we mean just generically by compression. You could do that first and then the reflection across the x-axis, or the reflection across the x-axis and then the vertical compression. But first you have to do that. We suggest that you do the shifts on the horizontal, on the domain first, and then when you do on the range the vertical shifts, the vertical transformations, that you do the vertical compression and reflections in step 3, and finally you shift the graph up or down if needed. So if you look at it here, it has 4 transformations, but remember within step 2 and step 3, if you had reflections on both a negative sign in front of the x and a negative sign outside of the function, you could possibly have 6 transformations, and that's the most that you would have. When we look here, we have 3 transformations. The +2 is actually going to be a shift to the left 2 units. The negative sign outside of the function, the square root function, is a reflection across the x-axis, and the -5 is a shift down 5 units. So on a multiple choice test, that's what we're looking for. These different choices are going to have these orders they're going to have these transformations in the wrong order. First, where the +2 is bizarre, we shift our original parent function, which was f, to the left 2 units. Now, when we go to make our second transformation, we're not working on f anymore. We're working on the result of our graph from step 1. So here we want to look at the result, and we deal with this negative sign, which is a reflection across the x-axis. Then in our third step, we're taking the result from our second step. So again, by result, we mean the immediate resulting graph following that transformation. We go down 5. So it's only the first transformation that's affecting the parent function. After that, your answers are building on top of each other. That's why this order is important, to have it correct, to end up with the correct graph. If you do these orders and transformations in a different order, you may not end up with the same graph that we do following this order. All right, so here we're going to do these transformations on a point. So when we look at each transformation, we'll say, hey, is it affecting the x-coordinate or the y-coordinate? Is it acting in a normal way or in a bizarre way? So inside the parentheses is where we're going to start. We do shifts left and right first. So this 3, -6 is going to be transformed. That -5 is affecting the x-coordinate, but even though it says to subtract 5, it's bizarre. We're actually going to add 5. It's going to shift this point to the right 5 units. This 3, -6 is transformed to 8, -6. A shift to the left or to the right isn't affecting the y-coordinate. The x-coordinate controls left and right when you're plotting points from the origin. The result is this 8, -6. So we've taken care of that, shifting it to the right 5 units. Now, this 4 is a compression. The type of compression, it's bizarre. It's not a horizontal stretch, it's a horizontal shrink. Even though it says here 4 times x, we're actually going to take the x-coordinate and divide it by 4. 8 divided by 4 is 2. The y-coordinate is left alone for that transformation. Well, we're done with the transformations on x. our final x coordinate is going to be 2. These following transformations are going to affect this -6, this y coordinate. So we've got 2, -6. That froze up on me. And this 1/2 we need to do before we add 8. The 1/2 is a vertical shrink. It's like you expect. If you take half of the y value, exactly like it says. So half of -6 is -3. We now work with that result, the 2, -3. We're going to add 8 to the y coordinate. We're lifting this graph up 8 units. The y coordinate controls up and down. The x we already knew up here that it was going to remain 2, and -3 plus 8 is 5. So that's the point that we would look for among our choices. And of course they're going to have a -2, 5, or the change the sign, or they're going to do these transformations in a different order, resulting in a different point. They're not going to do it in the correct order. There's only going to be one correct answer among those multiple choice, and hopefully you can find it there. For this problem it would have been 2, 5. Alright, so remember that we had some word problems that were variation problems. Now, as much as students hate word problems, the variation problems don't have quite the same hatred, because you can look for key words. You find those key words and it's always the same. So the key words are varies directly, or directly proportional to. There's a key word, and that's the only key word that I see. So the variable here that I'm starting with, y varies directly with. That tells me multiplication. I have some constant that as x and y, as my values of my variable change, there's one number in this equation that remains the same. It remains constant. I'll figure out what that is in just a second. For right now, I'm just going to call it k. A lot of times they call it c for constant. I call it k. It says it varies directly with the square root of x. So here's the symbol. Radical means square root of x. So now they're saying that there's one data point when x is equal to 4, y is equal to 20. I'm going to replace the y coordinate with 20. I'm going to keep k, and x, I'm going to take the square root of 4. So 20 is equal to, well, the square root of 4 is 2, and 2 times k has to be 10. 2 times 10 is 20. Now, they wanted a formula. I started out with the formula, y equals k squared of x, but that's not going to be an answer, because there's enough information there to figure out what that k is. Among those choices, I'm going to replace k with 10. I'm looking for this formula. And now, if they change x, I can figure out and predict what y is going to be. If they told me that x was 16, the square root of 16 is 4, and 10 times 4, hey, y would be 40. And we can continue to, if it's not a perfect square when they give me an x, I can use the calculator and get a decimal approximation, but I can use this equation, this formula, to predict different y values if you give me the x value. Or if you give me y values, I can calculate x. We have another variation problem. This time we have 2 key words. We have this varies inversely, and we also have a varies directly. Okay, with directly we know to think multiplication. With inversely we actually think division. So on the left here, on the left side of the equation, they're telling me start with z, and they're telling me this z varies. It's going to change, and it's going to change as the values of x and y change. How it changes with respect to x, we're going to put that x in the denominator because it says inversely. What immediately follows that, I think division. Now my k, I'm just going to keep it either in the numerator, or I could simply put it out in front of my fraction if you prefer. The k is always going to be out there. It's never, the k doesn't follow with inversely, and that k is good for both of the key words. Now, varies directly. What's the variable that follows after the word directly? The cube of y. Now, it doesn't say cube root, it says cube. To cube y means to have an exponent of 3. There's the formula. I'm going to look among those choices, and if I see something similar to that, I suppose I could guess. But they give me enough information here with values of x, y, and z that I can figure out what number should be here for k. All right, they're telling when z is equal to 8, so on the left-hand side, let's write 8. I can figure out what k is. They're telling me y is 4. When I cube that, well, that's going to be 64, and x is 6. Excuse me. So I'm going to flip that and take this 8 and multiply it by 6 over 4 cubed. So 8 times 6 is 48. 4 cubed is 64. But hey, I can reduce that. I know that 8 divides both of those numbers. Actually, 16 divides both of these numbers. 16 goes into that 3 times. 16 goes into that 4 times. So this k up here, this guy, I know is 3/4. Now, they might write it as 3/4 times this other fraction, or maybe they put the numerator 3 times y cubed and in the denominator 4 times x. You know, I might have to algebraically manipulate my answer to fit the form of one of their answers to find the correct one. Here's another memorization. When we took a lot of time looking at the graphs of polynomials, and we noticed that the end behavior, that when you get very far away from the origin, these polynomials behave in one of 4 ways. Given the equation, you can predict which one of these your graph is going to look like. When your degree is odd, if you have something f of x is equal to some 3x to the 5th, an x to the 4th, minus an x cubed, maybe there isn't an x squared or an x term and it just says plus 1. We're only interested in the term that has the biggest exponent, okay? So if that exponent is an odd number, then I know my end behavior is going to go in opposite directions. This odd is either going to be choice C or choice D. Those ends are in opposite, those are going in opposite directions. With a positive leading coefficient, if you had, you know, a 2x to the 5th plus, I don't know, some junk, versus if you had a negative 2x to the 5th plus, you know, some other junk. Well, that leading coefficient is positive, so you're going to pick the one that has the positive slope. A positive leading coefficient, this guy is C. An odd degree with a negative leading coefficient, this one is D. Here you're going, as x is increasing, you're going down, so that the slope of that is negative. Here, as x increases, you're going up, and that slope is positive. All right. Now, with an even degree, your end behavior is either going to go up together, like y equals x squared. You see how if you have f of x is equal to x squared, that exponent is even, so the tails go together. The leading coefficient is positive, so it's going up. If you had a graph that was negative 1 times x squared, that's a parabola that opens downward. So here it'll be an even degree with a positive leading coefficient. This is A. And an even degree with a negative leading coefficient, like negative 1 times x squared, that's going to be B. So you know that these questions are going to be on there, but either these are going to be shuffled, or the choices are be shuffled, or both. But if you memorize that A and B have to be even degree, C and D have to be odd degree, positive is up, negative is down, positive is up to the right, negative is down to the right. List the list of possible rational zeros. Here I have a polynomial function, and this polynomial may or may not cross the x-axis. If it does cross the x-axis, it might be at a rational number like 2/3 or 5, or it could be an irrational number like the square root of 5. I have a theorem that helps me find the x-intercepts only when that those x-intercepts are rational numbers. So like I say, it may not cross it at all, or every time it crosses it, it could be irrational. This list might not provide any x-intercepts, but if it does have a rational x-intercept, it's going to be in this list. So first, make sure that this is in standard form. By standard form, the exponents are in descending order. 5, 4, 3, 2, 1, the constants last. Let's look at the factors of that constant term. This constant term, whether it's 2 or negative 2, doesn't matter because we put plus or minus in front of our factors. 2 is a prime number, so the list of factors is plus or minus 1, plus or minus 2. Now, this guy is the possible numerator. The leading coefficient, that's another prime number. When you're doing these problems, boy, you hate those large composite numbers like 12 and 36 that has a long list of factors. Because if you're actually using this theorem to find out which ones are x-intercepts, you then do synthetic division on every single number until you find a remainder of 0. So you like it when that list is short. Alright, so plus or minus 1, plus or minus 3 is my possible denominator. Now I'm ready to find the list. If my denominator is 1, then I've got 1 over 1 and 2 over 1, which is just 2, and plus or minus in each one. So when you divide by 1, hey, you get these numbers back. Now I'm going to divide by 3. We have plus or minus 1 divided by 3. I'm going to have plus or minus 2 divided by 3. So if there's no guarantee that this graph even crosses the x-axis, but if it does, and if it's a rational number, it'll be one of these. So it's not a real powerful theorem because there are a lot of ifs, but it is pretty useful. Alright, let's take a look here. Now, if 1 and 2 are a 0 of this function, let's take a look at 1. If we plug in 1 and do the arithmetic, you'll get 0, but at least that's what that says. Or if I do synthetic division, 2, negative 3, negative 5, 13, negative 6. I'm expecting a 0 here. If I don't get a 0, I've either done an arithmetic error or there's a typo in the problem and there's something wrong with the problem statement. Alright, so let's practice our synthetic division. This 2 comes straight down. 1 times 2 is 2. Add these together, get negative 1. You multiply by that number in the box if it's below the line. That's negative 1. That's negative 6. 1 times negative 6, negative 6. That's 7. 1 times 7. We've got a problem. If I haven't done any arithmetic errors, I was expecting this number to be a 0. I think there's a typo. Well, I know it's a typo. It's a lie. This 1 is not a 0 of this function. Since this guy is not 0, this graph does not cross the x-axis at x equals 1. Let's take a look and see if 2, if it could possibly be an x-intercept or if it's also a typo. Alright, we're expecting to see a 0. Something's wrong if we don't have a 0. Either we've done our arithmetic error wrong or interpreted the theorem wrong, or, like I say, there's a typo. The 2 comes down. 2 times 2 is 4. We add these together, that's 1. 2 times 1 is 2. Add those together, get negative 3. Multiply that, get negative 6. That's 7. 2 times 7 is 14. 14 minus 6 is 8. So there's no way, I know I've done this correctly because somebody asked about it today in 7th period. This is not a 0. So I went back and I thought, well, maybe I can use my list and go through and check these values in a list, create a list for this problem, and check and see if I can find a 0. Now, see, the intent of the problem was to give us those numbers so we didn't have to do that as a time saver on a test. All right, let's look at this list. The factors of my, this is in standard form, 4, 3, 2, 1 in the constant term. The factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. The factors of my leading coefficient, 2 is a prime number, it's just 1, plus or minus 1, and plus or minus 2. So this guy was the list of possible numerators, my constant term. This is the list of possible denominator. So let's take a look at the list. So if each one of these guys are divided by 1, you just get that list back again. So I've got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, because all I did was divide by 1. Now when I divide by 2, I'm going to get plus or minus 1/2. But 2 divided by 2 is 1, and I've got that already in my list. 3 divided by 2, plus or minus 3 divided by 2. 6 divided by 2 is 3, and I've already got plus or minus 3 in my list. Well, if this graph crosses the x-axis, and if it does so at a rational number, it'll be one of these values. Well, I took time in 7th period, checked every single one of these numbers, and I did not get a 0. So it was a perfect example of going through the list and not finding any rational zeros. I went to that online graphing calculator, that Desmos, and I graphed it, and when I looked at the graph, it did cross the x-axis, but it did so at irrational numbers. We don't have techniques to find those irrational zeros. So what I've done, since this is an important problem, I made a problem. Here's a correction. I corrected the typo. Instead of this being plus 13x minus 6, if we use this 2x to the 4th minus 3x cubed minus 4x squared plus 3x plus 2, it should work. So, pause the video, see if you can find verify that these two are in fact zeros of the function, and then use it to factor this completely to find the remaining zeros. And remember that a 0 could cross the x-axis, or it could do a touch and turn, and that means it has a different multiplicity. So try that, see what you get, then compare your answer to mine. Okay, now if 1 is a 0, if I do synthetic division, and let's hope that I did correct the typo and haven't compounded it, the 2 comes down, I multiply by 1, I add, I multiply by 1, I add, I multiply by 1, I add these together, I multiply by 1, and I did get a 0. Alright, now what's nice about the synthetic division, if 2 is a 0 of this original expression, this 2x to the 4th, it's also going to be a 0 if this 1 now, this is 2x to the 3rd minus x squared. The powers have decreased by 1 since we divided by some power of x. We can come in and just use this 2 and do synthetic division again here, and we're expecting a 0 right there, or something's wrong. Alright, the 2 comes down, 2 times 2 is 4, 4 minus 1 is 3, 2 times 3 is 6, 6 minus 5 is 1, 2 times 1 is 2. Hey, I got the 0 that I was expecting. So that means that I can factor this f of x. Instead of writing this as this polynomial, that 1 in factored form is written as x minus 1, because 1 minus 1 gave me 0. This 2 in factored form is written as x minus 2. And this guy, this 2, 3, and 1, is a quadratic, 2x squared plus 3x plus 1. If I can't factor that, then the quadratic formula can tell me what the zeros are, because see, it wanted me to use this result from this synthetic division to find all additional zeros. We've already got 2 of them that were given, 1 and 2. This quadratic might provide 2 more. It could be that one of them is repeated. So let's factor it and see. Alright. We've got x minus 1 already, x minus 2 already. This guy, now maybe you should use the x method. It's got a leading coefficient that's different than 1. The middle term is 3x. The first term times the last term is 2x squared. Two numbers that multiply together to give me 2 but add up to give me 3 are 2 and 1. Multiply them together, you get 2x squared. Add those together, you get 3x. If we put this information in the body of a table, it can help us factor it. The 2x squared, the first term, and the last term go along one diagonal. The two values that I found in my x go along the other diagonal. It doesn't matter whether I put the 2x in this corner or that corner, we'll still get the same answer. So if I get 2x and 1x there. If I look and factor horizontally, these don't have anything common. They're relatively prime, so we say, hey, they just have a 1 in common. And 1 times 1 is 1. Now here, these guys don't have a coefficient common, but they do have an x in common. And if I look at it vertically here, they have a 2 and an x in common, so this is 2x. So this guy factors to 2x plus 1 times x plus 1. Alright, so I don't see any. At first I thought that that this would be the same as that, but that's x minus 1 and that's x plus 1. So let's construct a table. Here we have our zeros that we can list and their corresponding multiplicity. And then just to remind you, we'll talk about whether it's a cross or a touch and turn if you were looking at the graph. Alright, so we've got 4 zeros. Well, I'm going to have to shrink that up, give myself some more room. Talking to an empty room right now. It feels weird all the time to be in here talking, doing these math problems with no one here. Alright, so I've got, what do I have? X equals 1. Put in 1, do that multiplication, you'll get 0. If x equals 2, 2 minus 2 is 0, do that multiplication, you'll get 0. Subtract 1, divide by 2, if x is equal to negative 1/2, that'll give you 0, and when you multiply it'll give you 0. Over here, x is equal to negative 1. Since these exponents are all 1, the multiplicity for all of these is 1. Had we had an exponent of 2, the multiplicity would have been 2. Since these are all odd numbers, when you look at the x-intercept, the graph crosses the x-axis. It's when those multiplicities are even that it does a touch and turn. So it crosses, it crosses, it crosses, it crosses. Now, although it didn't ask for that, I thought, hey, I'll just give you that information for free. Alright. So here we have a polynomial equation. I don't have any sharp corners. I don't have any jumps. It's fallen into one of my 4 categories. The end behavior is going to either positive infinity or negative infinity. Here it's going down to negative infinity. Here it's going up to positive infinity. Alright, so how can I figure out what the equation of this would be? Well, I know that the leading coefficient, the degree on that first term, on that leading term, is going to be odd because the end behavior is in opposite directions. Remember that multiple choice with all those pictures that we had of the possible cases. So we've got down and up. Alright, so I know my degree when I'm done with this is going to be an odd number. I know, since as you move from left to right it's going up there, that the leading coefficient is going to be a positive number. Had this been going up and had this been going down, it would have been negative. But this leading coefficient, I don't know what value it'll be, but I know it's going to be positive. Alright, so in factored form, let's call this, since it's a polynomial, let's call it p of x. This graph has an x-intercept here at -5, but in factored form, you write it as x plus 5. Because when you plug in negative 5, when you substitute negative 5 for x, negative 5 and positive 5 give you 0. Now, notice that how it intercepts the x-axis is that it crosses it. So I know that this exponent should be an odd number. Now, let's shrink this up a little bit. Let's go on to the next factor. Here at negative 2, write it in factored form, it's x plus 2. Because when you replace x with negative 2 and positive 2 give you 0. But notice how it's doing what we call a touch and turn. Sometimes they just call it a touch. It comes down and just grazes the x-axis and then turns. I call it TNT, a touch and turn. That's going to be an even multiplicity, an even exponent. All right. Move on to the next factor. Here at positive 3. In factored form, that's written as x minus 3 because replace x with 3, 3 minus 3 gives you 0. Again, it's a touch and turn. This is going to be an even value. If you take an odd number plus an even number plus an even number, guarantee it that it's going to be odd. So far, I don't have any contradictions at all. Now, I can pick any odd number I'd want, but I'm going to pick the lowest values and stuff. Instead of a 3 or a 5, I'm just going to pick a 1 right there. So x plus 5 is going to be to the first power. This x plus 2 as an even number could be a 4, a 6, or an 8, but hey, I'm going to pick a 2. And this guy, this x minus 3, I'm going to pick a 2 also. Now, one little hint about these even and odd, I'm pretty confident that that's a 1. If it was a 3, when it would come in and intersect that 5, it would do it kind of flat and then come in. You know, the bigger this exponent is, the more it tries to come in and be constant right there, but it just never quite is constant. But you see it kind of flatten it out a little bit right there, the bigger that exponent is for odd ones. Now for the even ones, I know that these guys are probably the same magnitude. I suppose they could be both be 4 or both be 6. But like if this were a 2 and if this were a 4, when it does the touch and turn, it's a little bit flatter as well. You know, it's more of a, but again, it's not really getting, it's only touching the x-axis once, but it's really, the bowl is really wide there. It's really flattening out there. Since I don't see that, I'm pretty confident that 1, 2, and 2 would be correct. And I know that among the choices, this x plus 5, you're going to see even numbers, or the x plus 2, you know, you're going to see odd numbers or an even and an odd. There's only going to be one answer that has this odd, even, or there should be only one. All right, so here on number 36, boy, this guy's asking us a lot of things, so we're going to have to break it down. On the test, it won't ask you this many things on one question. It'll just say find the vertical asymptotes, and it'll give you the choices. Then on the next question, might be the same function, and says find the horizontal asymptote. I'm going to do my preliminary work here. I'm going to start out by factoring both the numerator and denominator of this function. So x squared minus 4x minus 12 factors to x minus 6 and x plus 2. Both of these numbers have a factor of 3 in common, and when I factor that out, I've got x squared minus 4. Well, this is x squared minus 2 squared, a squared minus b squared, so that factors. So I've got x minus 6 times x plus 2. I've got 3 times x minus 2 times x plus 2. Now, since these are factors, when you have this factor divided by that factor, it's equal to 1. So we say it cancels. So this original function is equivalent to this function provided that x is not equal to negative 2. Negative 2 is not in my domain because you would have never been able to reduce it if this is negative 2 and positive 2 would be a 0 in the denominator. So I know that this function is equivalent to that function as long as x is not equal to -2. Alright, so even though it doesn't ask it, I'm going to start out with finding the domain. Since it's not asking it, I'm not going to bother writing it in interval notation. I'm just going to quickly observe that 2 minus 2 gives me 0. I want to avoid that, so I don't want x to be 2. -2 plus +2 gives me 0. I don't want x to be -2. When you throw numbers out of the domain, if it's a rational function, then on the graph, it'll show up in one of two ways. You'll either have this x equal 2 being a vertical asymptote, or you'll have it being the x-coordinate of a hole. There's a hole in the graph, maybe. How do you determine which is which? Maybe they're both vertical asymptotes. Maybe there's two holes in this graph. Well, you look at what got reduced. What got reduced was x plus 2. Those canceled. So this -2 plus 2, it's this guy that's the x-coordinate of a hole. And this other one, and really I should say when x equals -2 is the x-coordinate, because not equal to -2 meant that it wasn't in the domain. We threw it out of the domain, and at x equals -2, you're going to see a hole in the graph. At x equals +2, we're going to put in a dashed line to represent a vertical asymptote, because this guy in factored form remained in the denominator, and so the line, the vertical asymptote, is a line, and the equation of that line is x equals 2. Alright, so the hole has an x-coordinate of -2, and we're going to have to figure out what that y-coordinate is. We can go ahead and do that now. How do you figure out the y? Well, when you have a function, the input is the x and the output is y. But we already know if we plug in a -2, -2 squared is 4, and 4 minus 4 is 0, and we're not going to get a y value. But what if we ignore that when x is not equal to -2? Because see, this hole, this is not a point that's on the graph, it's a hole in the graph. That point is guaranteed to not be on the graph. If I plug in a -2 into this reduced function, if x is -2, I've got -2 minus 6, I've got 3 times -2 minus 2. This numerator is a -8. This denominator is 3 times a -4. Alright. Negative divided by negative is positive. 8 over 4 is 2. So I have 2/3. So this y-coordinate for this hole is 2/3. Hey, kind of cool, huh? I think it's cool. So, the values that got excluded from the domain were either a vertical asymptote or the x-coordinate of a hole, or both, or one or the other, you know. So let's make sure now that we try to answer these questions. Did we find a vertical asymptote? Yes, it had a vertical asymptote, and that vertical asymptote was the line x equals 2. So our vertical asymptote was the line x equals 2. Have we found a horizontal asymptote? Well, no, we haven't thought about that yet. To find the horizontal asymptote, you compare the degree of the numerator against the degree of the denominator. Well, the degree, you only use that leading term. This is in standard form. It's this x squared. It's that 2. The degree of that numerator is 2. The degree of this denominator is 2. So when you compare the degree of the numerator against the degree of the denominator, it's either going to be top heavy, bottom heavy, or in this case, they're equal to each other. When they're equal to each other, you create a fraction with the leading coefficients 1 over 3. So the horizontal asymptote, had it been top heavy, there would have been none. Had it been bottom heavy, it'd be the line y equals 0. But they were equal to each other. Degree 2, degree 2. It's the line, well, you create a ratio of the leading coefficients, and it's 1 divided by 3, 1/3. All right. We've done the vertical asymptote, we've done the horizontal asymptote, x-intercept and y-intercept. To find the x-intercept, you let y be 0, the output of the function. The output of the function is f. If we say, does this fraction ever reduce to 0? I'm going to write this in factored form. I'm going to use, let's see, I'll use my reduced x minus 6 over 3 times x minus 2. I want to be careful. I don't want to accidentally say that one of these values is an x-intercept when it's not even in the domain. There is no corresponding y value, so at 2, there's no point on the graph, there's no y value. At -2, there's none. So when I look at the function, I want to use the reduced function after I have factored and simplified my expression. All right. If a fraction equals 0, it's because the denominator will never be 0. So I do have a variable in the numerator, x minus 6. X equals 6 is the x-intercept. Some people like to give the location of that x-intercept on the x-axis. The point in two-dimensional space would be 6, 0. Go to the right 6, but don't go up or down. There's the x-intercept. To find the y-intercept, let's change colors here. Oops. To find the y-intercept, we let x be 0. We plug in 0 into the function. So I don't have to use my reduce. I'm going to use this guy, not the one in factored form, because it's easy to see. If x is 0, then 0 squared is 0. 4 times these two terms are 0, and I have a -12. If this guy is 0, 3 times 0 squared, hey, that's 0. I've got a -12. I know that -12 divided by -12 is 1. So y equals 1 is my y-intercept. If you look on the y-axis, it would be at a point that we call 0, 1. You don't move left or right from the origin, you just move straight up. So there's both my x-intercept and y-intercept. The ordered pair of the whole. Well, we already answered that. We have the whole occurs in this graph at -2, 2/3. All right, so we've answered that. That's all. We've done it all. All right, let's move on to the next one. Okay, they're giving us the same directions. Oh, no, this is I've copied and pasted the same problem. Guess what? If I did this, I'd get the same answer for 36 that I got right here. Better pay attention to what I'm doing. 37. Hey, now I have a similar problem like before, asking me the same questions. It's getting a little bit late in the evening. I'm going to call this for Skill 5 Part 1, and I'll start with this 37 for Skill 5 Part 2. I'll do that in the morning because I still have some things to grade and to look at. It's getting difficult to keep up and catch up and get all this stuff done by the end of the year. But you guys are having a hard time as well. So hang in there.